started here. I'm Paul Adams. I'm director of the Fort Hays State Science and Mathematics Education Institute. At least that doesn't mean I have other hats, but that's my hat for tonight. And I want to welcome you to our 90th Science Cafe. We're counting down to the 100, and we're beginning to start the plans for that in September of 2019. For those that have been to Science Cafes before, welcome back. And if you're new here, this is just an opportunity to hear something new, interesting, exciting science. We've covered this year from in the ground to above the ground to burning fields to just about everything. But we're heading back now to go take us, as April will finish up our academic year, so this will be the last academic year, to take us out into deep space and hear about that and finish stuff. So we do appreciate you coming, and at the end, if you haven't, we do the big door prizes, so that's a great thing to do. And we can also share with you some things we do have planned for the summer and what we're looking towards for the 100th cafe. So we're fortunate to have a repeat presenter, and we're trying to decide if it's been once or twice, one time before, two times. Anyway, what's that? Somebody said two? Okay, Cheryl said two.
She's always right. So
she's always right. She told us we've been doing this since 2008. So with that, without me going on any further, I'd like to introduce from the Department of Physics at, Kansas State. I'm sorry.
That's okay.
We can make an honorary Fort Hays person.
Okay, thanks.
But from Kansas State University, Dr. Maranta, who's a distinguished professor of physics, and his topic tonight, I'm not saying more about it, dark matter and all things we hear about next. So let's please welcome to Fort Hays.
Thank you. It's really nice being back here again. So can you hear me, or should I be using this mic? Or okay. So I wanted to make a couple of announcements. So this Saturday is March for Science, and we're having one in Manhattan. And if any of you are there, you're welcome to join in. And you can see this on the K-State Physics webpage. And we also have a really great talk on the 17th. So if anybody's in Manhattan, then it's going to be in Cardwell in room 101 at 4:15, and there'll be cookies at 3:45. So I'm a cosmologist, so I'm interested in the largest scale objects. So I work on the structure and evolution of the universe. And I find this really interesting because of the usual story. We've had great improvements in technology, and we have great new telescopes both on the ground and in space. And there's also been really great improvements in detector technology that allow us to capture a lot more of those photons, the electromagnetic radiation that comes in, and turn that into electrical signals that can be analyzed by much more powerful and faster computers. And we've got two really striking results. They've been around for a while, but they've got very strongly confirmed in the last decade or so. So the first one, I think most of you are probably familiar with this. When we look out and measure all the contents of the universe at the present time, we can measure the amount of atoms and molecules and the stuff we're made up of, and that constitutes only about 4.5 or 5% of the stuff out there. So 95% of the stuff that we know exists, we have no idea what it is. We don't know what kind of particles make it up or what it is. And so if you're interested in a big puzzle, that's a pretty huge puzzle. So if you kind of think about times in the past when people didn't know what was out there, I mean, one example is for the Europeans. When Columbus set out, they didn't know what he was going to find. And Columbus had a pretty good idea of the size of the world, and he knew he'd just double it and double the known world in size. So that's a factor of 2. We're talking about a factor of 20 now, so we hardly know anything of what's out there in the universe. And the other result that's probably going to be even more profound and striking is that we know from these cosmological observations that either quantum mechanics or Einstein's theory of relativity are incomplete descriptions of reality, and they need to be improved upon. And that's pretty striking because they've governed, quantum mechanics and relativity have governed pretty much all of physics for more than a century, for maybe 110 years, 115 years now. So we're coming up to a pretty big revolution in physics, and it's going to be really interesting. It's kind of unclear whether it's going to happen in the next 10 years or the next 50 years or the next 100 years, but something's going to happen. Oh, and I just want to point this out. I put a bunch of cards on your table. So those are produced by a friend of mine who kind of studies how people understand numbers and scientific facts. He's a professor at UC Berkeley. And that website that's on there is a really interesting website, so you might want to look at it. Okay, so this is my backyard. It's also sometimes called the Conza Prairie. And we have about 300 bison there. It was bought by the Nature Conservancy, and it's run by K-State Biology. And Kansas is a really interesting state. We have about 2.8 or 2.9 million people and 6.4 or 6.5 million cattle. So about 2 cows per person. There's not that many states that are that way. But the Conza is a really nice place, and you can go for hikes. So has anybody gone hiking here? If you put your hands up. And you can leave them up if you've gone 10 kilometers. Well, so like that's about, I don't know, 8 miles or so. Anybody gone 80 miles or 100 kilometers backpacking? Like 1, 2. Anybody gone 1,000 kilometers? Okay, so so there are kind of limits to how far you can go. I guess if you're really, really patient, you can go 1,000 kilometers. Okay, so maybe if you could reach up and touch your hair and take one strand in your fingers and kind of feel it. I mean, just reach up. So do you think you can feel something thinner than a hair? Are you sensitive enough? I mean, that's kind of the limit, right? So that's about, for a typical person, that's 1/10 of a millimeter. I'm sorry I'm using this metric system, but that's kind of what we use in science. So your hair, so that's a meter, so that's the typical human size. So I'm probably a little bit under 2 meters, so a meter is about 3 feet. You can go down to 1,000th of a meter, which is a millimeter, and if you go down one more factor of 10, that's sort of the thickness, the diameter of your typical hair. And if you walk, so a kilometer is 10 to the 3, so that's 100 kilometers. So that's sort of the distance you've gone if you've hiked a lot. So that's kind of the range we're restricted to with our human senses of touch. So we can't feel stuff that's much, much smaller than maybe 1/10 of a millimeter. And it's really difficult to go much, much bigger than 100 kilometers. But there's a lot of stuff going on at much, much smaller scales and at much, much bigger scales. And you can kind of go down and look at biology and biophysics and biochemistry and then atomic physics and molecular physics. And you look at the atom, and inside the atom you see this nucleus, which is a factor of 10 to the 4 smaller than the size of the atom. And if you have enough energy, you can collide things, and you can break up the nucleus, and you see it's made up of protons and neutrons. And you can collide protons, and you can see that they're made up of quarks. And so you kind of go down, but you cannot go down there and touch stuff with your hands. You've got to build machines. You build microscopes, or you build big particle accelerators like the ones at CERN. And you have to interpret what you get out of there. So you have these machines, they have detectors, and you collect that stuff, and you build mathematical models, and you kind of start believing in these models if they can predict things. The same thing happens on really large scales. You can't go out to many tens of thousands of kilometers. And so you've got to use a telescope and collect the light that comes in and then interpret that in terms of mathematical models. So all your intuition about how the world works has been developed over a very, very narrow set of length scales. You kind of throw balls and you develop Newton's laws. And there's no guarantee that those laws are also going to apply at really tiny scales or at really large scales. And in fact, they don't. So at really tiny scales, you've got to deal with quantum mechanics, and at really large scales, you've got to deal with relativity. So it's probably not unexpected that both those scales are governed by laws of nature that are very unintuitive, because you can't develop that intuition through rolling balls and throwing things and colliding things that are macrophysical that you can touch and feel with your hands. And so you've got to develop this intuition, and the way you develop is you trust your machines and you collect that data and you build the mathematical models and then make them predictive, and that's how you start developing intuition on these scales and on those scales. And so I want to talk much more about this side because that's where I want to end up. And it's really difficult to appreciate how big the universe is. So I'm going to start out in human scales, and for those of you who went to school a while ago, I have to tell you that we've changed our units. So instead of this old-fashioned unit of a meter, we now use an Einstein, and a meter is half an Einstein. So I can do this in terms of lengths. I can also do it in terms of masses or ages, but I don't have time, so I'll focus on lengths. So this is a really nice picture. This is Africa. And that's the Indian Ocean, that's Madagascar. And pictures like this only became possible maybe 50 or 60 years ago when we started launching satellites with cameras into space. So I'm going to take my Einstein, I'm going to go to my store and buy Einsteins. And I'm going to have to buy a bunch of them. So what I need is 6.5 million Einsteins. If I pile them one on top of each other's shoulders, and I'm going to end up with a pile of Einsteins that is as long as the diameter of the Earth. So you go a factor of about 10 million or so when you go from the scale of an Einstein to the scale of Earth. And Earth's a pretty small planet. We can take another step, and this is a step of another factor of 100 in length. And this is the sun through a certain filter. I guess we're kind of cutting off the top. But the sun, to get the sun, you need to go to your store and buy 700 million Einsteins, so a factor of 100 more Einsteins to get them on each other's shoulders to get the diameter of the sun. And the sun is a slightly bigger than average star. It's nothing really spectacular. So we can turn some of this into numbers, and numbers are sometimes useful, so I'm going to do this. So if we want to go to larger scales, we can look at, so I don't know if I really need this. Am I loud enough, or should I be using this more? Okay, so I don't know if I can shut this off. No, I probably don't need to. So we're going to look at the Earth's orbit around the sun, and that's approximately a circle. It's really an ellipse, but it's pretty close to a circle. And the Earth-Sun distance in terms of meters is another factor of 100 compared to the diameter of the sun. So it's 1.5 into 10 to the 11 meters. And it's getting to be a pain to carry around so many powers of 10, so we want to try to introduce a new system of length units. And there's two conventions to do this. So the people who study planetary systems and solar systems kind of take the Earth-Sun distance as the standard, and they call that the astronomical unit. And that's just the unit of length. So you can measure distances to other planets in terms of the astronomical unit, which is the radius of the Earth's orbit around the sun. There's another way we can do this, and we can do this by realizing that light has perfected the art of cruise control, especially when it's traveling in a vacuum. So light always travels at exactly the same speed when it's in a vacuum. So if it's not going through a medium, if it's not going through glass or something, if it's in a complete vacuum, it travels at almost exactly 3 times 10 to the 8 meters per second. And so you can think about how long it would take for a light signal to travel. So if I tell you Manhattan is 180 miles from here, I can also tell you that if I'm traveling at 60 miles an hour, Manhattan is 3 hours away. And you can do the same thing with light. I mean, my driving, I might not stick to 60 miles an hour perfectly all the time, but light always sticks to the same speed. And so you can measure distances in terms of how long it takes light to travel that distance. And if you look at the Earth-Sun distance, it takes light about 500 seconds to travel that distance. So I can say that the Earth-Sun's distance is 500 seconds. So I don't have to use the old-fashioned meters. I can either use an astronomical unit, or I can use the light travel time, which is 500 seconds. So we can go out and look at bigger collections of objects. So the next thing I want to look at is this nearest neighboring star to the Sun, which is the Proxima Centauri. It's a triple, so it's got a couple of other stars tied to it gravitationally. But some of you have probably heard about Proxima Centauri because it's been in the news in the last year. It's the closest star to the Sun that has a planet in the habitable zone. So when you say a planet is in the habitable zone, that means that it's not too close to the star to have lost all its water, and it's not so far away from the star that all its water has turned into solid ice. So it's at a distance where you can have liquid water, and people think you need liquid water for life. So that's why Proxima Centauri has been in the news. So Proxima Centauri, it's a factor of 10 to the 5, 100,000 further away from the Sun than the Earth is from the Sun. And if you want to think about light travel times, if you have a light signal, you pulse it at Proxima Centauri, and think about when it gets to the Earth, it takes about 4 years for that light signal to get to the Earth. In terms of AUs, it's 200,000 AUs away. So we're starting to get back many powers of 10, and it becomes kind of messy. So people who study collections of stars don't like using the AU. They prefer a new system of units. And the abbreviation for that length unit is the PC. The name is the parsec. And that just stands for a parallax of an arc second. And the definition, it's a little complex. So what you do is you take your observer and back her out so that the angle, the Earth-Sun distance subtends at the observer is 1 arc second. So an arc second is a really tiny angle. So if you go around a whole circle, you have 360 degrees. And each degree you can divide into 60 arc minutes. And each arc minute you can divide into 60 arc seconds. So an arc second is a really, really tiny angle. So you've got to go really, really far for this distance, this huge distance, to subtend 1 arc second at the observer. And that distance is then the parsec. In terms of light travel times, it's about 3¼ light years. So it's roughly the distance to Proxima Centauri. So Proxima Centauri is about 1 1/3 of a parsec away. We can look at numbers to objects that we're slightly more familiar with. So we have the moon, which orbits the Earth, and the moon's the furthest we've sent humans, and that's about 1 light second away. So it's really, really close by, even compared to the distance to the Sun. So it's 1/500th of the distance of the Sun from us. If we want to go out, so we're still in Kansas, so Pluto is still officially a planet. And I mean, because Tombaugh was in Kansas, so we can use the Sun-Pluto distance as the size of the solar system. And so Pluto is about 40 AUs away, 6 times 10 to the 12 meters. So if you want it in light travel time, it's about 6 hours away. So those pictures you saw from the New Horizons mission, I guess it was year before last, that spaceship sent them to Earth, and it took 6 hours for that signal to come to Earth, and then it took some processing after that. But that's sort of the size of the solar system, or maybe the solar system's a little bit bigger if you want to define it in terms of how far Voyager is from us. The furthest we've ever sent anything are the 2 Voyagers, and I think last year was their 40th anniversary. So Voyager 1 is about 140 AUs away, and we're still getting signals from it. It's about 19½ hours of light travel time away. So we can kind of get an idea. So it took 40 years to get out to 140 AUs. So if you want the speed of Voyager, it's 140 AUs divided by 40. So it's about 3½ AUs per year. And that's pretty fast. But when you kind of think about the distance from the Sun to the nearest star, if you're going at 3½ or maybe even 5 AUs a year, this is 200,000 AUs, and so we're talking about 40,000 years for something like Voyager to get to that star. And so if you have much better technology, maybe you can send something in 20,000 years to Proxima Centauri. So when people talk about sending astronauts to nearby stars, I mean, you can kind of think of what's involved. the astronaut will have to travel for about 20,000 years at least. And so there's a bunch of options. You can improve medicine tremendously and stretch the human lifespan. The other thing you could do is build a huge, huge spaceship and put a lot of people on there and allow them to reproduce. And then 200 generations later, somebody human will land up there. And to make sure that that person is still human, you probably need to have a lot of shielding of that spaceship so you don't get cosmic rays interfering with your biology, and you'd have to put a lot of food on that spaceship. And so clearly, we do not have the money or the resources to do that, so we're not going to send astronauts to stars anytime soon. So that was our nearest star. We live in the Milky Way, and if you know where to look at certain times of the years, you can see it. An artist's impression is a little bit clearer. So it's a collection of stars, and when you're looking at it from the side, it's a disk. If you're looking at it from the top, it's a pizza. And there's probably about 200 billion stars in the Milky Way, or maybe a bit more. And the typical star is a little bit smaller than the sun. The sun is not that much bigger than average. So we have a pretty huge object. So the diameter of the disk is about 50,000. So kilo stands for 1,000 parsecs. So the distance to the nearest star to the sun is about 1 parsec. So the size of the Milky Way is 50,000 times that size. So if you want to convert this into light travel time, you multiply by 3¼ and so you're talking about maybe 160,000 years. So if you have your rocket that can take you at the speed of light, which you can't, I mean the only thing that can travel at the speed of light is pretty much light. So if you start out a light pulse here and send it across, it'll take about 160,000 years to get across. So it's a huge object. You can see this black stuff over here. That's not the absence of stars. That's the presence of dust, like little dust grains. And there's as many stars in the black patches as there are in the shiny patches. You just don't see them because the dust absorbs that visible light. And because of conservation of energy, it's going to have to re-emit. The dust heats up and it re-emits that light in the infrared. And so if you had infrared eyes, you could see light being emitted by the dust. So there's also a big halo around here, which is maybe, it could be as big as like 10 times the size of our galaxy, and it's mostly made up of dark matter. But it's got these little globular clusters in here. And these guys are collections of a few 100,000 stars, and they kind of orbit the galaxy. They're outside the disk part of the galaxy. So that's the main part of our galaxy. We can look at our nearest neighboring galaxy, and then you go out even further. So this is Andromeda. If you know where to look, you can see this at certain times of the year. It's also a spiral galaxy. You can see the bulge in the center. You can see the disk. You can see the dust lanes. And it's a little bit bigger. So this is about 60 kiloparsecs, 60,000 parsecs, and maybe a little more than 200,000 light years across. And these two guys are actually little dwarf galaxies with a few 100 million stars that are bound to Andromeda. So they're orbiting Andromeda just like planets orbit the sun. And so Andromeda is about 2 million light years away from us. So our galaxy is a little bit under 200,000 light years. When you go to the distance of Andromeda, you're going another power of 10. And when you look up at the sky and you look at Andromeda, that light that hits your eye left Andromeda 2 million years ago, and it's traveled in a straight line and went through the lens of your eye, and you hit your retina, and it got converted into electrical signal in your brain, and you saw the image of Andromeda. So it was traveling for 2 million years. And if you go back in time 2 million years, I mean the big thing that happened maybe about 3¼ million years ago, or 3 million years ago, was Lucy in Ethiopia. She fell out of a tree and killed herself. And she's an early ancestor of humans. So that's kind of the time scale, about 2 million years ago. So this is one little galaxy. Galaxies, some of them at least, are like people. and they like hanging together, and they pull on each other through Newton's inverse square law of gravity, and they form these big collections that are called clusters. So this is the central part of a nearby cluster. It's the Virgo cluster. So the scale here is a few million parsecs, so maybe about 10 million light years. So the distance to Andromeda is about 2 million light years. This is about 10 million light years. It's the central part of the Virgo cluster. The whole Virgo cluster is probably about 30 million light years across. And each of these spots of light you see here is a galaxy. Each of them has maybe 200, 300, 150 billion stars. So this is a huge object. The central part of the Virgo cluster, there's probably about 2,000 galaxies here. There are a couple of special ones, like this guy, for instance. So at the center of the cluster, just like the sun is at the center of our solar system and the other objects are moving around it, the central guy is pretty heavy. And we can kind of understand why he's so heavy. So if you kind of think about satellites around the Earth, the low satellites are going to run into the Earth's atmosphere, and there's going to be drag and air resistance and friction. And they start losing their kinetic energy, the energy of motion, and they come lower and lower, and eventually they hit the Earth. A galaxy also has an atmosphere. And if there's a nearby galaxy that comes near it and that's somewhat smaller, it'll spiral in because it's going to be dragged in by the resistance of the atmosphere of the big galaxy. So this guy is a cannibal. He eats galaxies. He eats all his nearby neighbors. And it's got maybe 500 or 600 billion stars. So a typical galaxy like the Milky Way is probably 200 billion. So this is a big object. But it's a pretty insignificant object on the scale of things. So this is a little patch of the universe. So we're in our disk galaxy. We're about 1/3 of the way out, and we're looking up at the outside of our galaxy, so we don't look through the dust in the disk of the Milky Way. And we're looking at kind of a cap on the sky and looking at all the stars in there and all the galaxies and everything else. And this picture was taken at the Lick Observatory by Shane and Vertanen in the 1950s and 60s. So they have this telescope there. They would take their glass plate and put emulsion on it and put it at the focus. And they'd take little photographs, and many thousands, maybe a few thousand photographs. And then they'd put it together. And they sat there, and so if any of you have kids in college or in school, if they complain about homework, you can tell them about this story. So this is in the 60s, the early 60s and the late 50s. They didn't have access to fast computers. So they sat there by hand, and they looked at their photographs, and they figured out the positions of 400,000 galaxies by hand. And then this map was made later by a group at Princeton. So the scale here is about 1 billion light years. And this kind of tells you what the distribution looks like on this scale. So this guy is a cluster of galaxies, that little dot, that's the Coma cluster. It's about 120 million parsecs away from us. It's got maybe 7,000 or 8,000 galaxies in it. Each of those galaxies has maybe a couple of 100 billion stars. And it's just one little dot here. So you can see a lot of other clusters, and you can see regions where there's fewer galaxies, and you can see filaments. So if you want to think about this, so these regions with the fewer galaxies, there really are fewer galaxies there. It's not that there's dust there that's obscuring galaxies that are hidden in the dust. There's not much dust in these regions. So these regions are called voids. And the way to think about this picture is to think about the bubbles in your bubble bath. So the voids are the interiors of the bubbles. The galaxy is like living on the bubble surfaces. And where two bubbles run together, you get the filaments. And where more than two bubbles is where the filaments kind of drain together, you get the rich clusters of galaxies. So that's how this matter is distributed on this scale. And it's kind of interesting. It's not that different than what we see in this room. So if you look to your right or your left or above you or below you or in front of you, you see something very different each time. So a distribution like that is said to be anisotropic. So if you say a distribution is isotropic, that means you're standing at one point and you're looking around you in all directions and it looks exactly the same. This room is manifestly anisotropic. Haze is anisotropic. You can go to the top of a tall building and you look in certain directions, you see certain buildings. You look in other directions, you don't see the same buildings. Our Earth is anisotropic. In some areas there's an ocean, in other areas there's a mountain range. The solar system is anisotropic. You look in one direction, you see the sun, and you look in any other direction, you don't see an equally big nearby star. So even on this scale of 1 billion light years, it's pretty anisotropic. You look over here, you see very few galaxies. You look over here, you see many. You look over here, you see very few. So in different directions, you see different things. And so this is not terribly surprising. What's kind of surprising is that when you go out another factor of 10, and this is the Big Bang, the biggest scale we're going to look at. So this is a picture of the afterglow of the Big Bang. So what we're looking at here is electromagnetic radiation. So there's a telescope out in space that's collected this electromagnetic radiation that's come in. And it looks in all directions on the sky. So you're looking at the interior of a sphere, and there's some depth to that sphere, so you can see through part of it. And to show you that, I've cut it from the North Pole to the South Pole and opened it out and squashed it on this plane. So this edge has to be identified with this edge. And you do the same thing when you try to put a globe on a flat piece of paper. You slice it and you open it out, and then you get the American continent over here, and Europe and Africa, and then Asia, and Japan would be over here, and maybe also partly over here. You kind of fold it back together. So this is just the temperature of that radiation that comes to us. And it's in the microwave part of the electromagnetic spectrum. It's the same kind of radiation you use to cook food at home, and that police use to give you speeding tickets. So it's microwave radiation, and you can measure the temperature. It's very, very cold microwave radiation. So if you measure the average temperature, it's 3 degrees Kelvin, which is the absolute temperature scale. So it's 3 degrees above absolute zero. So room temperature is about 300 degrees Kelvin. So this is very cold radiation. And they've been able to measure the difference between the colder spots and the hotter spots. And the difference is very, very insignificant. The color scale has been tremendously stretched so you can see the difference. The difference between the blue cold spots and the red hot spots is 30 millionth of a Kelvin. So it's 30 millionth of a Kelvin, and the average is 3 Kelvin. And so the difference is 1 part in 10 to the 5, or 0.001%. So when you look at the temperature over here, it's the same as the temperature over here. It's the same as the temperature over here, to 1 part in 100,000. So it's very, very similar. So this distribution is very isotropic. So this scale here is maybe 4,000 or 5,000 megaparsecs. If you want to turn that into light travel time, that's maybe about 20, say maybe about 15 billion light years. So maybe 15 times bigger than the whole scale over here. So when you get out to 5 to 10 to 15 billion light years, the universe looks the same no matter what direction you look in, provided you're looking on those length scales. But when you get down to your local neighborhood, it looks different in different directions. So these are 2 really important facts about the universe. So your local distribution near you and on smaller scales, the matter distribution is not uniform. It is anisotropic in space. But when you start comparing things over length scales of a few billion light years, it looks the same. When you compare patches of the universe that are of the order of a few billion light years, it doesn't look different in different directions. And these are 2 really important facts. I'm not really going to get into them further, but there's a model that describes the evolution at very, very early times, and it's called the inflation model of the universe. And that model can account for both these facts. So I'm going to move on to something that's even more bizarre and even more difficult to get a handle on. which is this. And so clearly, if the universe is expanding, that means we've got measuring devices that are not expanding. So we've got something that's not expanding that we can use to measure the expansion. And so it's kind of important to understand why our measuring devices are not also expanding with the universe. So our measuring devices are typical ones, maybe a meter stick. And so we want to try to understand why that's held together and it's not also expanding. So on the scales of the meter sticks and on the scale of the universe, you have two important forces. So I've got a little cough drop here, and it's got some mass. And if I don't support it, Earth's gravity is going to pull it down. So Earth's gravity pulls stuff down. That's what gravity does. If you have two masses, they're pulled together. And gravity is an attractive force. You also have electromagnetism. So you can kind of think of this as charged particles like electrons and protons. So if you have two electrons, they have the same charge, and electromagnetism pushes them apart. If you have two protons, they have the same charge, and electromagnetism is repulsive. But if you have a positive charge and a negative charge, a positively charged proton and a negatively charged electron, electromagnetism pulls them together. So like charges attract, unlike charges repel. And electromagnetism is way, 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 way stronger than gravity. It's pretty much responsible for a lot of things in everyday life. It's what prevents you from falling through the chair you're sitting on. So if you kind of think about your chair, it's made up of atoms, and atoms have this electron cloud, and inside, a factor of 10 to the 4 smaller, they have a nucleus. But everything between that electron cloud and the nucleus is just vacuum. There's nothing there. So it's kind of, in some sense, a puzzle as to why you don't just fall through that, right? Because there's nothing there. So you can kind of think of what an atom does. So it has this electron cloud, and the electrons are negatively charged. And then you have another atom on this side that has an electron cloud. And electromagnetism tells you those guys don't like each other because they have the same charge, and so they're going to be pushed apart. But then there's atoms on this side of them, and those guys are going to push this way. And there's atoms here that are going to push them here, and there's atoms here that are going to push them here. So they have nowhere to go. So all that electromagnetic repulsion just makes things really rigid. So they can't move. And that's why matter is rigid, and that's why you don't fall through the chair, even though it's mostly empty space. And it's why you don't fall through the floor when you walk on it, even though it's mostly empty space. I mean, there's hardly anything there except the nucleus and an electron cloud. And electromagnetism is really, really strong. If you take two protons and ask how much gravity pulls them compared to how much electromagnetism pushes them apart, electromagnetism pushes them apart by 36 powers of 10 stronger than gravity pulls them together. So electromagnetism is so strong, but if you kind of think about it, I mean, you're made up of atoms, right? So do you think you're pulling on your neighbor electromagnetically or pushing your neighbor apart using electromagnetism? I mean, you're not, because unless you really vigorously combed your hair today before you came in here and built up some charge on you. Because if you didn't do that, you're made up of atoms, and atoms have the same number of positive protons as they have electrons that have negative charge. So you're made up of the same number of electrons and protons. So the pushing and pulling you do on your neighbor electromagnetically gets canceled out. But you're pulling on your neighbor gravitationally. So as you get to bigger and bigger scales, matter is neutral electromagnetically, and so the electromagnetic force gets less and less important. But you pile on all the mass, and gravity gets more and more important. And then when you get to the scale of galaxies, gravity is by far the dominant force. And so we've got to use the best model we have for gravity, which is Einstein's theory of general relativity. And what that does is something that's kind of bizarre, because all your intuition has been based on Newtonian physics, which you kind of developed by rolling balls around in this room or in whatever room you took your physics class. So what Einstein did was, so Newton kind of said there's space and there's time, and everything happens in this fixed unchanging space, and time kind of evolves uniformly, and you evolve in time. So you can collide two balls and they bounce off and they do things. but space and time don't take part in the physics of that collision. And Einstein said if you want a more accurate description of reality, both space and time have to take part when you're colliding those guys. And so he made space and time part of physics, and so space can change and time can change in time, and space can get bigger and smaller and do all kinds of really strange things. And that's really difficult to appreciate. So what general relativity does is it kind of goes in and sneaks into regions of the universe where there's not that many galaxies, and it creates more space there. And that space has to go somewhere, and it spreads out. And the galaxies are embedded in that space, and they go along for the ride. And this is just really, really difficult to appreciate. And so you've got to sit down and think about it and go to Google and go and look at Scientific American articles and Discover articles and kind of think about it. And I've got a couple of toys here. So here's my space. It's a one-dimensional space. And I've put a wave on it, so you can see a wave. It's got peaks and troughs, and it's got a wavelength or a pitch or whatever you want to call it. And this is not exactly what gravity does, but let me just go ahead and do it. So I'm going to make my universe expand. And if you look at the wavelength gets bigger and bigger as the universe expands. And as the universe contracts, it gets smaller and smaller. Right? So the wavelength is kind of the distance between two similar points on the wave. So it gets bigger when the universe expands, and it gets smaller when it contracts. So gravity is not sitting there and pulling space. It's going into the regions in space and creating new space and pushing this stuff apart. But I can't get a demonstration of that, so I've got this demonstration. The universe doesn't expand in one dimension. It expands in every dimension all at the same time. So it's not just one-dimensional expansion. But if you have a light wave that's propagating in an expanding universe, so when you have a short wavelength, if you're talking about the visible part of the spectrum, that light is colored blue. And when you have long wavelength light, that's red. So you know that even longer wavelength electromagnetic radiation is infrared, and shorter wavelength electromagnetic radiation is ultraviolet. It's even bluer than blue. So if you start out with blue light and you have a star that emits blue light, and that light travels to you as the universe expands, it turns into red light. And that's what people saw, and that's what led them to this clue that the universe is expanding. So we have to kind of decide how we're going to talk about this expansion. So I've got to introduce a variable to describe the universe. And in this case, it's just going to be the distance between my hands, and I'm going to call that the scale factor. And as time goes on, the scale factor gets bigger and bigger and bigger. And that's what's telling me that the universe is expanding if I want to turn this into mathematics. So I've got this picture up here. So I've got my elastic band, and my scale factor is this distance. And physicists call that A. That's the scale factor, and it's a function of time. And as time goes on, it gets bigger and bigger. And as the universe stretches, the wavelength stretches. And the wavelength, which is the distance between these two peaks, and you can kind of think about it, and it's pretty straightforward. It's going to grow in proportion to the size of the universe. It's going to grow in proportion to the scale factor. And a lot of people who do spectra and atomic spectroscopy, they kind of prefer talking about what they call a redshift, which is this variable z, and it's just the ratio. It's 1 plus the redshift is the ratio of the size of the universe now, if that's the size of the universe now, to the size in the past when it was younger, and that you can turn into a redshift. So at the present time, the redshift is 0, and as you go back further and further in the past, the redshift gets bigger and bigger. So as you go forward in time, the scale factor gets bigger. As you go back in time, the redshift gets bigger. So that's some of the expansion of the universe. It was discovered by accident by this guy, Slipher, and he was working at Lowell Observatory in Flagstaff, Arizona. So how many of you have gone to Flagstaff? It's just south of the Grand Canyon. Anybody been to Lowell? Okay, so you know there's another telescope that's related to Kansas there, right? So Tombaugh's telescope, where he discovered Pluto, is also there. So you can go see both these telescopes. And if people have questions at the end, I can tell you how this is related to intelligent life on Mars. But Slipher used this telescope, which I have over here also. Had he collected light from a bunch of external galaxies, passed that light through prisms and diffraction gratings, and broke it up into its colors, into spectrum. And he realized he could identify the atoms that produce that light because they all have characteristic spectra. And then he went into his lab and he looked at the spectra those atoms produce in his lab. And he realized then that the spectra that he collected from these distant galaxies was redshifted compared to the spectra he produced in his lab. And he didn't know what to make of it. But you know this effect. If you've ever listened to an ambulance or a police car go past you, it's called the Doppler effect. So when something's moving, when it comes towards you, the pitch goes up. When it goes past you, the pitch goes down. And so Slipher saw that the pitch was going down, and so he concluded these objects were moving away from us. And so there's two options. The obvious one is that somebody lit a big firecracker and shot all these galaxies out, and we live at the center of the universe. And that's a reasonable thing to think about. But if you want an isotropic universe, that's not going to work because it's going to look the same. I mean, it'll be isotropic about one point, but I'll come back to that in a little while. So actually what's happening is that every point is moving away from every other point in the universe. So you might ask whether our Milky Way galaxy is taking part in this expansion. Does it get bigger and bigger? And it doesn't get bigger and bigger, and most galaxies don't change in size because of the expansion. That's because they're held together by a stronger part of the gravitational force, which is Newton's inverse square law. And you can use that, and you can see that the galaxies don't expand. So the galaxies are like the ping pong balls here, and the black stuff in between is space, and I'm creating more space between them, but the galaxies do not expand. They just get further and further apart. And this is, we'll come back to this a few more times and talk about it. But so this is another toy model of the expansion of the universe. So I've got a three-dimensional model here. So these are all one-dimensional. So what I've got here is a three space. So I've got just like this room. So there's a vertical dimension and two horizontal dimensions. And I've got a part of my three-dimensional universe. And you can kind of think about it. It's pretty clear that it's got to go out to infinity in all dimensions, because if it didn't, and you went out to the edge and looked out, it wouldn't look isotropic. It will look different outside than it looked inside. And so if you want a universe like this, it's got to be infinite in extent. And I've put down a bunch of galaxies over here, and you can go ask your observers what they see. So if you ask your observer on number 3 what she sees, she'll tell you she sees every galaxy move away from her as the universe gets bigger. And you can go ask your observer on number 6 what he sees, and he'll tell you the same thing. So any galaxy is an equally good position to be at the center of the universe. And so none of the galaxies are at the center of the universe. Every galaxy is moving away from every other galaxy. So this is just Hubble's law pretty much. We'll come back to that in a second. But if you kind of think about the size of this universe, as time goes on, you get expansion in that dimension, that dimension, and that dimension. So each of them has a scale factor. And if you want the expansion to be isotropic, the scale factors have to be the same. So the volume goes like A cubed. So this is really bizarre, so I'm going to try to show you a few more demonstrations. And as long as the people nearby have liability and medical, I don't have to worry too much. You guys in the back, don't worry about this. So this is my universe. It's a two-dimensional closed universe. So there's nothing inside of it. There's nothing outside of it. You're an ant. You live on the surface of this. And these are my galaxies, these red dots. They're stuck on. They don't expand with the expansion. But if you kind of look at a galaxy, say you live on this guy over here, and you think about light coming to you from another galaxy. So by the time it reaches you, the universe has got bigger. So if it started out bluish, it'll become reddish. And if you think about light from a further away galaxy coming to you, it has to propagate through a longer distance. And so it becomes even redder. And if you think of a guy even further away, that propagates over a longer distance. So that's why people talk about redshift. So the nearby guys hardly redshifted, and as you go further and further away, they're redshifted more and more. And there is no center to this. I mean, I couldn't get a perfect balloon, so you can ignore this neck. But if you go anywhere else, any observer on any galaxy is going to see the same thing. And so maybe I should stop this before I kill too many people. So that's the expansion of the universe, and that just gives you Hubble's law. So what Hubble did was he measured the distances to these galaxies, and it's really difficult to measure distances. So he took Slipher's galaxies and measured distances, and if people are interested, I can talk about this later. But so he discovered this really nice law. So Slipher got the speeds the same way that police Doppler radar get your speed. They take a microwave signal, they bounce it off your car, and then the signal comes back, and they know the pitch they send it with, and they know the pitch they get back. And so Slipher did that with atoms. So he knows the pitch at which the hydrogen atom emits light, and he knows the pitch at which he collected that light, and so he can get the speed of that galaxy. So he measured this, and Hubble measured the distance, and he found that when you double the distance, you go to a galaxy twice as far away, it's moving twice as fast. You go to a galaxy 3 times as far away, it's moving 3 times as fast, and so on. And this is just the uniform expansion of the universe. You can look at the data here. So this is the speeds at which the galaxies are receding from us in kilometers a second. That's 10,000, 20,000, 30,000. And we can forget this residual plot down here, but the distances to the galaxies are over here. So you can go to a galaxy 100 megaparsecs away, and it's moving at about 7,000 kilometers a second from us. A galaxy 200 megaparsecs away, it's moving at about 14,000 kilometers a second. And this is Hubble's law, this red line. It's kind of the best fit to this. So the speed of recession is proportional to the distance that galaxy is at. So that's the Hubble expansion. And so then the next step is to kind of think about the whole universe. And one obvious thing we can do is generalize what Copernicus did with the solar system. So Copernicus said that we're not that special, and we should probably put the center of the solar system on the sun, because that's the heaviest object. And you can do that with the universe and say we're not that special, but there is no heaviest object there that we can place at the center of the universe, so any object is equally good. So we say that the universe is homogeneous. And the reason we say that is we go and ask your friendly neighborhood observer on Andromeda what she sees when she looks at the universe on the scale of a few billion light years. And she's going to tell you she sees an isotropic universe. And you can go and ask your friend who lives in the Virgo cluster what he sees, and he's going to tell you when he looks at it on the scale of a few billion light years, he sees an isotropic universe. So if you have observers at different points in space seeing that the universe is isotropic, then that universe is homogeneous. So a homogeneous universe has much more symmetry. So let me first explain homogeneity. So if I'm standing here and I look around me and I see everything's the same, that's isotropic. But if I translate myself in space and then look around me and see it's also isotropic, the only distribution that can do that is a homogeneous distribution. And if you want to see a really simple homogeneous distribution, when you go home, put on your scuba suit and jump into your gallon jug of milk and swim around it. So when you swim around it, as long as you don't get to the walls, no matter where you go, it looks exactly the same shade of white. So you can translate yourself in that gallon jug of milk, and that's a homogeneous distribution. So the universe is, so we kind of assume this is the equivalent of the Copernican principle, that it's spatially isotropic for all observers, so it becomes spatially homogeneous. And then we kind of have this very, very symmetric universe, and there are only really 3 options. So I can't show you the 3-dimensional universes. So I've shown you the first guy, the sphere. So it's just this balloon. You live on the surface, it's a compact universe, and it has no edges. So that's called a closed universe, and it's said to have positive curvature. You can also have a flat universe, and that's like the top of this table, except it's got to go out to infinity in both dimensions, because if it didn't and you looked out, it wouldn't look the same when you looked in, and it wouldn't be homogeneous, it wouldn't be isotropic. So a flat universe has got to be infinite, and like you can have a positively curved one, you can have a negatively curved one, it's saddle-shaped, and that's called an open universe, and it's got negative curvature. So these are our three options, and the dynamics, I mean, the easiest way to think about it is to think about the radius of this balloon, and that's sort of the equivalence of the scale factor. So as time goes on, that radius gets bigger and bigger and bigger, and the surface gets bigger and bigger because it gets stretched. And that's our dynamical variable. That's the scale factor. So we need to start doing a little bit of math, and we have to write down an equation that tells us how that scale factor changes. So this is kind of the generalization of Newton's F equal to ma. So if you can identify what you're looking at, so if you have a ball and you're kind of rolling it and there's the force of friction, so you plug in your F on the F side, that's the friction force, and you know the mass of the ball, and that A is the acceleration. It's the rate of change of speed, and speed is the rate of change of distance. So your dynamical variable there is you choose an origin, and it's the distance that ball has rolled, and that's your dynamical variable. And the speed is how fast that distance changes, and the acceleration is how fast the speed changes. So we want the same kind of equation for our scale factor, and we know that the universe is expanding, so everything is moving away. So we know that there's a positive speed. So when we're doing physics, the symbol for the rate of change of something is a dot. So if you're looking at A, then a dot is the rate of change of A. So the speed is positive, so this is the expansion rate or the speed, and that's positive. 2 minutes, okay. And the next thing you might want to look at is the acceleration, and this is the acceleration equation. And so I can kind of cut this short because I've only got 2 minutes. So basically, this acceleration equation, if you have normal matter, then the universe is going to decelerate. And then people went out there and they measured the acceleration, and they found that it accelerates. And the only way you can get that is to postulate a hypothetical substance called dark energy. So I don't have time to do that, but I'll just kind of stop here. And if people are interested, I'll hang around a little bit and try to explain dark energy and dark matter a little bit more. So all I got to was the expanding universe so far. Sorry. Thank you.